Hello, everyone. Thank you for joining me here today. This video is about learning how to build a machine learning model for demand forecasting. Demand forecasting is one of the classic use cases for time series modeling. So this could serve as an intro for any type of time series modeling that you might want to do using machine learning. My name is Sylvia, and I work as a data scientist at Stemly. Stemly is a startup that provides autonomous decision science in the supply chain and finance domain, and it's based here in Singapore. I work in the customer success team in the data science division, where I interact closely with our customers, translating their business needs into machine learning models. My main focus is to build forecasting models for our customers. Thus, using one of the projects I worked on in the last year, we will learn how to apply machine learning to forecasting. There are a lot of similarities between building a machine learning model for time series and any other task that you might be familiar with, such as classification or regression. The steps are always data processing, feature engineering, hyperparameter tuning, validation, and analysis of the prediction. The main differences in this case lie in the feature engineering, validation, and analysis stages. We do them a little bit different, and that's what we're going to cover in this presentation in the next few slides. So let's start with the data understanding. The project, again, is a supply chain project. So for those of you like myself 2 years ago, do not know much about how our favorite products end up on the shelf or on your Amazon cart, let's take a look at a simple diagram of the supply chain. So here we can see the flow of goods from the raw material to the consumer, passing through the supplier's hand to then in the factory of the manufacturer and their warehouses, to then be distributed by the distributors to the retailers, and then where they are bought from the consumers, by the consumers. So in this project specifically, we want to focus on the link between the manufacturer and the distributor. And we will refer to the flow of goods between manufacturer and distributor as shipment quantity. So our task is to forecast how many units the distributor will ask for me, the manufacturer, for each product at the daily level for the next 12 weeks. So we're going to have our historical data, and we're going to come up with a forecast time series. So, and hopefully those two are as close as possible. But how do we get started? So before we dive into which model will do best and show off all of our knowledge into the most complex deep neural networks, let's understand which factors influence our target variable. So forecasting is indeed a little bit of an art, and is currently done in most companies through relatively simple technology, but relying on years and years of personal experience of the demand planners. So the key here is understanding which factors will end up affecting our demand. For example, what will you consider first if you wanted to know how many bottles of shampoo the distributor from Malaysia is going to ask tomorrow? So one of the things that you might want to consider is how much quantity the distributor will be selling to the retailer and how much it's sold in the past. I might want to consider how many I have on hand, because depending if I have 0 bottles of shampoo, I'm probably going to not ship anything today until I refill from the supplier myself. And similarly, the distributor is not going to ask me for any shampoo if they have abundant inventory on their own warehouses. And all of these quantities that we talked about are themselves influenced by price, promotion, and market conditions. So our task is to identify how to encode all of these moving parts into a data structure that is understandable by our machine learning model. So how do we do it? Let's take a look at how time series data is encoded. So for each row, we have a unique ID and date combination. And for each ID and date combination, there's a target variable, our volume in this case. The ID from the table that we're seeing is the product ID. And you can use the ID or the date or both to join in any type of other information that you might want to have, like product information, price, location, temperature of the day, or whatever you prefer. But how do we encode the sequential nature of the time series? That's where lags come in helpful. Lag 1, for example, is the quantity that we've sold yesterday. Lag 2 is the quantity that was sold 2 days ago. So similarly, you can calculate a lot of other features based on the time series itself. We call these time series features or intrinsic features. Like, for example, here you have a diff column, which is just the difference between yesterday's and today. That can also be useful depending on what you're trying to forecast. So again, it's really important to understand what people currently do when they do the forecast. What affects the demand? You're going to have to make a hypothesis and then run some analysis to verify that your hypothesis is correct and it validates your choice in features. Analysis is super important here. Is your data seasonal? Is it intermittent or is it smooth? Based on your analysis and based on your hypothesis, you'll choose the best matching features. So these are some examples of features that we might want to consider. The external data features, we kind of talked about it already. So the sellout, inventory price, promotion, master data containing all the product attributes and so on, market data, weather. And then you have those additional intrinsic features that we also talked about, like the lags or any statistical measure that characterizes the distribution of the time series. Like, what's the maximum, what's the minimum of that time series? Or maybe just a moving minimum, moving maximum, or other examples of intrinsic features that you can have listed here. No matter which feature you consider, you should always ask the following questions. First of all, the time frame. For each date and ID combination, which quantity of the feature do you want to consider? For example, consider sellout. Do you want to consider the same date value for the sellout? Or do you want to consider the cumulative value for this week for that sellout? Or maybe you might want to consider the value of the sellout 28 days ago, because maybe your goods have a 28 days lead time. These are all very important questions to ask. And that's where a conversation with your business owner is really important. Another question that you might want to ask is relevance. You can understand the relevance of each feature using, like, for example, in a tree-based model, right? You have the feature importance as an output after you train your model. So is the feature importance what you expected? Is it what the business expert expected? And if not, does it make sense why the relevance is as it is, if you take a look at the data? If not, I think there's something wrong. You go back to feature engineering and try to troubleshoot. There might be a bug there. Another thing that's super important is questioning the availability of that feature at prediction time. For example, you use weather data to do the forecast of umbrellas, for example, because the sales of umbrellas are strongly related to the weather. However, if you will need to forecast next month's daily sales for umbrellas, then you will be required to know the weather then. How are you going to do that? What is your uncertainty on the weather forecast? That's going to affect the uncertainty on your umbrella sales forecast. What are the implications of that? Think about it very carefully. So now you have your features, but do you really know how your model works? If your model works, that's when we need to compare the forecast at the actuals. Some of the error metrics that we use in time series forecasting are very similar to what you might have seen in regression, for example. So we have our classic MAE, the mean absolute error, where we take the absolute value of the difference between forecast and actuals, and then we take the difference. An example of an MAE value is 10. Then we have the root mean square error, RMSE, where we, instead of taking the absolute value, we square and then take the square root. That's the classic trick. An example could be 3.1, for example. So imagine going to your business, your customer, and you're saying, oh, my forecast has an error of about 3. Like, okay, what does 3 mean? It's not really business friendly. So what instead business owners love is mean absolute percentage error, MAPE. So in this case, you have a percentage value that you obtain by taking the difference between the forecast and the actual, but dividing it by the actual itself. And then you take the absolute value of that and the mean, of course. So here, then you will be able to say, my error is about 15%, which is, in business terms, a little bit more of a clear, it gives you a clear idea of what your error, how your error will have effects on the business. This is a metric that is hated by data scientists. And can you see why? Can you see what potential problems there might be there? For example, what happens when 80 goes to 0? You might remember from your high school or college days that if 80 goes to 0, then you have a division by 0. And no one likes to deal with infinities in their when taking a mean of different values. Another issue that we have with MAPE is that it treats under forecasting and over forecasting differently. They're not equally penalized. So that's why we have a lot of different metrics that might resolve that specific problem, like the symmetry problem, like symmetric MAPE, or the mean absolute scale error, which instead of taking the actuals, it scales the error by a benchmark number, a benchmark forecast number, like a naive method. Or you have WRMSE, which takes the power that comes with RMSE and makes it a little bit more business friendly by weighing it with the price of an item, or maybe the total quantity of an item. So no matter what metric you end up choosing, make sure that you have a close conversation with your business owner and understand what they are interested in minimizing. In our case, we use a proprietary metric that considers the actuals in the forecast for a time period. And that time period is related to the lead time of each product. So everyone does it a little bit differently. So now that we know that our model is performing fantastically with 10% MAPE or 90% accuracy, are we good to go? Well, not really. Let's make sure that this accuracy is going to stay. Usually, we do that in other tasks by doing cross-validation. Cross-validation can't really be performed on time series data because you can't pick dates randomly. Information from the future contains data from the past in the form of lags. So if I train my model on tomorrow's row, then it included lag 1, which is today's quantity. Therefore, if I'm putting today in the test set, my model already knows what today's value is. There are alternatives to cross-validation, of course, and we have two main options, the sliding window approach or the expanding window approach. So in both cases, you're forecasting on one fixed time period, which is depicted in orange here, and you're training your model on the period before that, which is in darker gray in the diagram. In the case of the sliding window, the period is fixed. So for every pass, you keep always the same size of the window and forecast on the orange side, while for the expanding window, you always augment your training period by a little bit. So no matter what technique you choose, make sure that the validation period is long enough to capture all the seasonality patterns that you might need. So you could stop now, but you probably have tried very different models and you realize that different models are better at different products. So maybe you have an LGBN model, for example, one of our favorites, that was trained only on shampoo, or maybe that was trained only on data from Singapore, and that might be better for products that are based in Singapore. Or maybe you build a very specialized model that is trained on shampoo in Singapore specifically. Maybe some other products really get forecasted perfectly by an ARIMA model, which is a statistical model, or an SES model. So what you could do is maybe choose automatically which model to use for each ID. Wouldn't that be amazing? I mean, you can build a model that chooses which models to choose. So these models are called ensembles. They're very meta, but they're very cool. The idea is to train very different models and put their error as training data for a stronger learner that decides based on the error which model to choose in the right circumstances. So this is when the more diversity you have in your ensemble, the better the accuracy. So make sure you use the most disparate model you can think of. This was our secret sauce on how we improved by 10% the client's already best-in-class accuracy. So hopefully you learned a little bit about defining forecasting model for demand forecasting or building a forecasting model in general. All of the steps that we took are actually quite standard for no matter what you're forecasting. And specifically, I hope you have some guiding questions in mind, which you're going to keep in mind when interacting with your own customer when building your own forecasting model. So it's time to test yourself out. Time series forecasting is really everywhere. Stock prices are time series as well. So imagine if you could crack that. It's definitely not an easy problem, but there's lots to learn along the way. So let's recap a little bit. So first, you should understand the business requirements and the structure of your data to maximize how you choose your feature and choose the best features. You make sure to validate your results to ensure that your accuracy is going to stay like this in the future as well. Bring in a lot of diversity in your ensembles, and not just in your ensembles, in your life as well. That's always good. And then optimize against the most relevant metric for your business. Really important. So do you have any questions? Drop them in the comments section below. If you want to learn more about time series forecasting, check out what we do at Stemly from our blog or our LinkedIn profile. And feel free to connect with me on LinkedIn and ask me any questions you might have. Good luck with forecasting.